Okay? So, moving on to page 5. So what happens if the population is not normally distributed? Well, let's run a couple simulations. So we're going to go back to StatCrunch and run some simulations. This time we're going to assume that we have data that's skewed right. And we'll use StatCrunch to approximate the sampling distribution of the sample mean, x bar, by collecting a bunch of samples of size 4 and size 30, just to try to figure out what's going on. So let's go back to StatCrunch and run these simulations. Okay, so again, we're going to go to applets. We're going to go to applets, sampling distributions. And the problem says, suppose that you have data that is skewed right. Okay, so we're going to have data that's skewed right. Okay, so I'm going to click on that distribution and say compute. Okay, so you get this distribution that's skewed right to begin with. For part A, we want to simulate taking samples of size 4. So I'm going to simulate taking samples of size 4. And again, right, this is going to simulate taking a sample. Notice that most of the values are over here on the left side of the distribution because this is a skewed right distribution. Anyway, but it simulates taking that sample of size 4, and then it drops the sample mean down here. I'm going to cut to the chase now and say, if we do this 1,000 times, remember what we're looking for is what happens down here. What is the shape, center, and spread of the green distribution down here on the bottom? So if I do this 1,000 times, I get something that looks kind of like that. This time, I'm getting something that it definitely looks more bell-shaped than what I started with, but it's still not exactly bell-shaped. Look at this long tail to the right. In fact, I would say that this is a skewed right distribution. If I look at the mean, though, the mean of my sample means is close to the population mean that I started with. So I think that mu sub x bar is still going to be the same thing as mu. If I look at the standard deviation of my sample means is smaller than the population standard deviation I started with. In fact, I think probably it's following the same rule. Like if I take this population standard deviation that I started with and divide it by the square root of 4, I'm thinking I'm going to get something close to this number, right? Let me use my calculator to figure that out. So I'm going to say, well, the population standard deviation is 11.8255. If I divide that by the square root of 4, then I get 5.91275, which is pretty close to what I have down here, right? So I'm thinking that this thing is still sigma divided by square root of n. So I think that's still true. But the distribution of my sample means is not bell-shaped. And in fact, I'll keep taking more and more samples. If I do this 20,000 times, then yeah, you can definitely see, right? We've got kind of a skewed right distribution over here. Okay. So that's worth writing down. Let's write that down. Okay, so the sampling distribution of the sample mean for samples of size 4. Well, the shape is not bell-shaped. It's skewed right. The center, mu sub x bar, appears to be the same thing as the population mean, just like before, which in my simulation was about 14. And the spread, sigma sub x bar, appears to be, again, the population standard deviation divided by the square root of the sample size. which, you know, in my case, this turns out to be about 5.9. Okay, let's do the simulation again for n equals 30, just to see if these patterns are still holding up. Okay, so I'm going to pull up another simulation, so applet sampling distributions. I'm going to do another skewed right distribution as my underlying population. And this time we want to simulate taking samples of size 30. Okay, so I'm going to do samples of size 30. And let's do this. Okay, so after collecting 1,000 samples of size 30, now this is the distribution that I'm ending up with. Maybe I'll do this 20,000 times. 20,000 times. So after 20,000 times, look at that distribution. Well, first of all, look at the mean, right? So the mean of my sample means is pretty darn close to my population mean. The standard deviation of my sample means, well, I bet if I take 11.8 and divide it by the square root of 30, I'm going to get something close to like 2.1, 2.2. Let's see. So 11.8255 divided by square root of 30 is 2.15903, right? Pretty close to this standard deviation here. So those two patterns are definitely holding up. But notice the shape of the distribution. This thing is pretty darn symmetric. This is bell-shaped now, right? We don't have any kind of right skewing that's going on anymore. This is just a perfectly symmetric bell-shaped distribution. So that's worth writing down for sure. Okay, so the shape of this distribution, when n is 30, the shape is bell-shaped again. So even though the population that we started out with was skewed right, the distribution of the sample means was still bell-shaped. Okay, so remember when I told you that there are a lot of phenomena in the real world that follow a bell-shaped distribution, that follow a normal distribution? Well, this is one of the reasons why. It's like, it doesn't matter what kind of population you're starting out with, whether the population is normally distributed or not, the sample means are going to be normally distributed. Okay, that's a really cool thing, and it's really, really useful for us. Okay, so the shape is bell-shaped. The center, mu sub x bar, is still pretty close to mu. The spread, sigma sub x bar, is still pretty close to sigma divided by square root of n, right? So those things are always true, right? Mu sub x bar is approximately the same as mu. Sigma sub x bar is approximately the same thing as sigma divided by square root of n. What happens to the shape of the distribution? Well, when n was small, when our sample sizes were small, the shape was still the same as the shape of the underlying distribution, right? Skewed right. But when n got larger, the shape became bell-shaped. So I'm going to say, as n gets large, so as n gets large, x bar becomes bell-shaped. Okay, that fact right there has a special name, and it's called the central limit theorem. This is a big deal in statistics, okay? So the central limit theorem says, regardless of the shape of the underlying population, the sampling distribution of x bar becomes approximately normal as the sample size n increases. One question that you might have is, well, exactly how large does n need to be in order for x bar to be considered normally distributed? And the answer to that is, it really depends on how badly skewed the underlying population data is, okay? But as a general rule of thumb, we'll say that x bar is normally distributed if one or the other of the following are met. If either the underlying population is normally distributed, or if the sample size is at least 30. Okay, so if our sample size is at least 30, then regardless of the shape of the underlying population, we can say that X bar is going to be normally distributed. Okay. Very good. So we'll cover the last page in a new video. Stay tuned. Oh man. Okay.